Okay, welcome to the class lecture 10, Engineering Metallurgy, phase diagram part 2. In the last lecture, we introduced how a phase diagram can be constructed for a binary system alloy, and for the alloy which is completely soluble in the solid state and the completely soluble in the liquid state. And today we are going to study equilibrium cooling of alloy of such an alloy which conforms to the phase diagram type 1, which is completely soluble in the solid state and completely soluble in the liquid state, and we'll analyze it for various alloy and how the alloy is forming. That we'll also look at that. So the type 1 diagram is about the equilibrium, so the binary system alloy. That means the both components are completely soluble in the liquid state and completely soluble in the solid state. So this is an schematic diagram for solid solution alloy, which conforms to the phase diagram type 1. In this case, we are considering two elements. One is element A and another one is element B. So in the case of element A, the melting point temperature is higher, that is here, and for that's here, that's the melting point temperature of element A. And I didn't include the other one because we're not going to consider analyze things on the other side. So the melting point of element B will be less than that. It will be somewhere here, in this location, where the element A will be 100. Element A will be 0%, and B will be 100%. So there are two lines. One is in contact with the liquids. So the liquids will be here. So this line is called liquidus line, and the bottom one is in contact with the solids, and that is called solidus line. That means the beyond the liquidus line, the alloy will be completely liquid, and below this solidus line, the alloy will be completely solid. And in between these two lines, the material will be, some portion of the material will be solid and some will be liquid. So this is a two-phase region. If you consider an alloy of 70A, 30B, that means 70% A and 30% B will be present in that alloy, which is shown in here. A vertical line will actually represent a single alloy. And we'll study how this alloy actually forms from liquid to the solid, and how the composition, that means the solid and liquid formation in the two-phase region occurs. We'll also study that one. The first, if we consider that the material is at very high temperature, that means both element A and element B are in the liquid state at temperature T naught, which is the temperature of the liquid metal, and both are completely soluble. So there will be, if you look at the microstructure in this case, it will be very uniform, and this is completely liquid. And since the alloy contains 70% A and 30% B, so the liquid solution will contain also 70A, 30B. And similarly, when the alloy completely solidifies and solidifies and the temperature drops below the solidus line at like this point, the chemical composition of the alloy will be same as 70A and 30B. But the chemical composition will vary from the liquidus line to the solidus line. Here, the solid percentage of solid and percentage of liquid will be different, and also in the solid part, the percentage of A and percentage of B will also be different. So when the temperature drops for this alloy slowly, if you cool the alloy very slowly and the temperature drops just below the liquidus line, indicating this point, that means the temperature is T1, and since this the temperature actually crossed the liquidus line, that means the alloy starts to solidify and it will form some solids or nucleus or some dendrites of the solid, and there will be some liquids will be present in there, and also there will be solid. But the formation of the solid, that means how much solid is formed, or what is the composition of the solid just below the liquidus line. If you want to know that, then we have to draw the tie line. If we draw the tie line means a temperature line, constant temperature line, which actually will give us the chemical composition at that temperature, as well as the percentage of solid and liquid present in that solution. So if this is the tie line, then the tie line intersects in the solidus line here, and if we drop this point below, then we'll be able to read the composition of the solid. Because when if the tie line intersects with the solidus line, that will give the point will give us the composition of the solid. That means which is 5% B and 95% A, that is indicated in here. That means the nuclei or solid that is formed just below the liquidus line, we can denote it as alpha 1. And alpha 1 contains 95% A and 5% B. And if we look at the liquid, the composition of the liquid will be like 69 A and 31 B, just here. Okay, it will be just very close to the alloy point, and that is 31% B and 69% A, chemical composition of the liquid. So we have found that the chemical composition of the solid that has formed at temperature T1, and also we have found the chemical composition of the liquid that has formed, that the remaining liquid is like 69% A and 31% B. And if you want to find the how much solid has been formed at temperature T1 and how much liquid has been formed at temperature T1, liquid is present in there, that can also be found here. Okay, how to find that? To find out the percentage of solid, if we want to find the percentage of alpha 1, which will be equals to, as you know, the lever rule. According to the lever rule, if you want to find out the percentage of solid, then we have to consider the intersection point at liquidus line. So the distance from this point to that point, this distance will give us the percentage of solid. So what is the distance? This distance is like 31B, since this point actually intersects at 31. So 31, if it is 31, then 31 minus, you can write 30. It like this, 31 minus 30. 30 is the alloy point. Okay, and to find out the total length of the tie line, then we have to go to here. That means that will be 31 minus 5. That will give us the percentage of solid developed, that means created during the solidification at temperature T1. And to find out the percentage of liquid, how much percentage of liquid is present, we can just simply make it like 1 minus percentage of alpha 1. Okay. To make it percentage, you can add 100 here, and then it will be 100 minus percentage of alpha 1. Or another way is that you can use the formula directly, to find out the percentage of liquid. Then we have to consider the distance from here to here. The distance will be from the alloy line to the intersection point in the solidus line. and that distance will be like 30 minus 5. 30 minus 5 divided by total distance is the same, 31 minus 5. 31 minus 5. That will give us the percentage of liquid present at temperature T1. Okay, any question here?
Sir, I have a question that
Okay.
why the liquid solution L1 has 69A and 31B? I
Why the
mean,
liquids?
yes, sir.
Okay, so when the solid forms, if you look at the formation of the solid, it has the solid is very rich in A, right?
Yes, sir.
And at the beginning, the liquid when at T naught, the temperature T naught, the liquid solution had like 70A 30B, and when the solid has formed, solid has 95% A and 5% B. So solid is very rich in A, and the liquid will subsequently be rich in B. Okay, because
Yes, sir.
most of the A are being used in solid. That is why it becomes like rich. Okay.
Yes, sir.
All right. Any other question? It will be more clear when we go to the next temperature. Okay. At temperature T2, when the temperature drops to the temperature T2, then we draw the tie line, and then we can find out that how much solid is present in here, okay, or how much liquid is present. And firstly, let us determine what is the percentage of solid in here. What is the percentage of chemical composition of solid? To find out the chemical composition of solid, we need to move to the solidus line. Okay, this point will give us the chemical composition of the solid, which is 90% A, 10% B. That means solid has, if you look at this here, the solid alpha 2 will have like 90% A. That means more solid will be created, and it will have like 90% A and 10% B. And if you look at the liquid solution, chemical composition of the liquid L2, which is 55% A and 95% B. That means when the temperature drops, the solid will have more B present in its crystal structure, and liquid will have more B present, and A will be reduced. Okay. And eventually this will be adjusted to the 70A 30B when the temperature drops. That means if we look at the next one, I think it will be more clear from here. This is alpha 1. Okay, that means this is alpha 1. That means the solid that has formed at temperature T1. At temperature T1, the solid dendrites or nucleus, whatever it is, the liquid will have like 69% A and 31% B, and the dendrites will have 95% A and 5% B. And when the temperature drops to T2 before diffusion, that means the alpha 2 has 90A 10B. How this occurs, if we want to explain that, that means once these dendrites are formed, dendrites of alpha 1 is formed. This is stable dendrites of alpha 1. When the temperature drops to the next level, that means a certain degree of temperature is dropped, then the solid that forms actually contains alpha 2, that means 90A 10B. Okay, and the previously formed dendrite like 95A 5B will be also present in this solution. Okay, in the solution that previously alpha 1 will also be present and alpha 2 will also be present. But by the time, since we are doing very slow cooling, the diffusion actually occurs. That means the atoms of B and atoms of A can diffuse through the solid to make the whole crystal of alpha 2 dendrites. Okay, that means when there is alpha 1, more atoms of B and more atoms of A are diffused into the dendrites of alpha 1 to form alpha 2. Okay, that is what occurs at temperature T2, and eventually at equilibrium temperature of T2 after diffusion, all the dendrites will be will have all the solid dendrites will be of solid alpha 2, and composition will be 90A 10B, and liquid composition will be 55A and 45B. Any confusion in here?
No, sir.
Sir, previous slide টাতে স্যার একটু দিলে ভালো হতো।
Yes. Okay.
এই হরিজন্টাল বারে স্যার যে কম্পোজিশন দেওয়া আছে 5 10 20 30 এটা তো এর জন্য দেওয়া আছে তাই না স্যার?
No, this is the
55%
weight percentage of B. Here
এই দ্বারা কি বোঝাচ্ছে স্যার? ওই যে নিচে
A is 100% here.
ও আচ্ছা।
A is 100%, and when B is 5, then A will be 95%. Okay, it's like this. Okay, then when the temperature again drops, okay, let's find out the percentage of solid at temperature T2 and percentage of liquid at temperature T2. It's very easy, isn't it? Like to find out the percentage. Like here, if you want to find out the percentage of solid, then we have to consider the length, this length, divided by total length. This length will be percentage of alpha 2. If you want to find out percentage of alpha 2, then it will be the 45 minus 30, 45 minus 30 divided by 45 minus 10. Minus 10 multiplied by 100%. This will give us the percentage of alpha 2, and if you want to find out the percentage of liquid, then it will be 100 minus percentage of alpha 2. Okay, that's how we found the chemical composition and the relative amount of each phases. That means the relative amount of solid phase and relative amount of liquid phase. Okay, when the temperature drops again to the T3, it will be similar, like the solid percentage of solid will increase and percentage of liquid will decrease. You can easily determine from the tie lines, like at temperature T1, solid percentage is very small. At temperature T2, the solid percentage is increasing. At T3, solid percentage is increasing more. And when the temperature drops again, then the solid percentage will be increasing and liquid percentage will be decreasing. And the chemical, if you look at the chemical composition, then when the as the temperature drops in the solid, the percentage of B is decreasing. Sorry, percentage of B is increasing according to the solidus line. Okay, and in the liquid, percentage of A is increasing. Percentage of A is increasing according to the liquidus line. When the temperature reaches T4, that means just below the just in the tie line. Let's say in the tie line or below or a little bit above of the solidus line. At temperature T4, most of the solid has been formed, but that solid will have a chemical composition of almost 70%. In here something is wrong. That means I have not plotted it accurately. Okay, I must have used a graph paper to do that. So it will not be like 100%, 75% A and 30B. It will be almost, okay. It will be almost 70A, 30B. That means less than 70A and greater than 30B. Okay, and then there will be liquid present at this line, and that liquid will have very high percentage of 65% B and 35% A. And when the temperature drops more, then the B is that 65% B from the liquid actually diffuses liquid. The percentage of 65% B actually from this liquid on the grain boundaries, the B atom diffuses to the solids. diffuses to the solids to make it 70A30B. And also when the B is decreased from the liquid solution, a percentage of A will automatically increase, and this will eventually become the 70A30B. And below the temperature T4, let's say at temperature T5, all the grains will have the chemical composition of 70A30B. Okay, any question?
T4 temperature, sir.
Before T4 temperature, at T4 temperature, just very close to the solidus line, it will not be 100% solid, because it takes time to become for the diffusion of atom A and B. Okay, element A and B, atoms of element A and B, the diffusion occurs in the solid state. That means when the temperature reaches T4, then the solid will have like almost 70A30B composition. That means which is the composition of the alloy, but it is not completely 70%, less than 70% A, and it will be like fractions, 69%, 69.5 or something like that. And to make it 70A30B, the amount of the B from the liquid solution actually diffuses into the solid solution, okay, in the solid alpha 4. And then it becomes 70A30B, and sorry, it will be more than 70 point something. Let's say it is 70.6, and rest of it will be the B. Okay, less than 30%. Okay, and the 65% B in the liquid solution, some of the atoms will be diffused into the solid solution to make the liquid solution on the grain boundaries. The liquid solution on the grain boundaries will become eventually 70A30B. When some of the B goes into the solids. And then when everything is 70A and 30B, then complete solidification occurs. Okay, and at the end, if you look at the microstructure of the solid solution, then you will get actually 70A30B chemical composition, and that will remain up to when the temperature is dropped to the room temperature. And the temperature is at room temperature, you will get only 70A30B composition and uniformly distributed on the grains. Okay, any question? Okay, then what is the significance here to study this? Why do we study like the equilibrium diagram of solid solution alloy? To explain that, we need to consider one thing, is that if you, let's say, heat this material, that is 70A30B alloy, if you heat this alloy up to temperature T2 and keep it for some time to reach the equilibrium, and then you suddenly cool it, then the chemical composition at this time at temperature T2 was, what was the chemical composition at temperature T2? It was 90A10B. Okay, and the liquid solution had the chemical composition 55A45B. If you cool it suddenly, very quickly, then the diffusion of A and B will not be facilitated. Okay, that means there will be no diffusion, and that is why at room temperature, what you will see is that there will be more grains formed in these locations at room temperature, and these white grains will have a chemical composition of 90A10B, and other grains will have the chemical composition of 55A45B. So to get a wide range of properties, if you cool it very slowly to the room temperature, then you will get uniform grains. All the grains will have the like 70A30B chemical composition. But if you cool it from temperature T2, then you will get the chemical composition of solid will be 90A10B. So this will give you a different mechanical, chemical, or electrical property compared with the regular 70A30B. So that is why we need to study this phase diagram to get wide range of properties. For example, when you cool it from temperature T2, then you will get this composition, and this composition will show a different mechanical property when you cool it from temperature T3. This will give you a different mechanical property. So between this temperature T0 to the temperature T4, you can have a wide range of mechanical properties of the same alloy. But if you cool it very slowly from temperature T0 to the room temperature, then you'll get only one property. Okay, and that is the significance of studying phase diagram to enhance the property. The same material, same element, same amount of elements A and element B, but you'll have different property because of the composition of grains. Grains will have different composition. Okay, a grain with 9810B will show a different mechanical property than a grain with 80A20B. Okay, because material A and material B is completely different. If you vary the percentage, then you will get different properties. Okay, did you understand?
Yes, sir.
All right. So how the diffusion occurs in the solid solution? Okay, to understand that, there will be 4 methods. Okay, or 5 methods actually. That's what we said. Like when at temperature T4, there will be grains, and grain boundaries will be present in there. Like the liquids are present in this region, and solids alpha 2, alpha 1, or alpha 3 is in here, and then the diffusion occurs in the solid state. That means some atoms of B actually penetrates into alpha 3, that is in the solid state. And how does it occur? There are various methods for that, like exchange. That means the atom in here, and there is an atom in here. This atom goes in the position of this atom, and then this atom goes to the position of the other atom. Okay, because of the vibration, because when the material at high temperature, then atoms vibrate, and they have kinetic energy, and because of that kinetic energy, the atom position of the atom can be changed, and that's called the exchange method for solid state diffusion. Interstitial, that means if the atoms are very small, then due to the vibration, these atoms can diffuse into the locations in any location. Okay, and vacancy, if there is a vacancy, and then the atom can move very easily from one position to another position. And interstitiality, that means the atoms trapped in the structure can move and can push another atom and take the place of that atom, and this atom moves further from the boundary to the solids. Okay, and there is another method which is called 4-atom ring interchange. That means the atom can this atom goes there, and that atom goes there, that atom goes there. Okay, by this movement, the atoms can be diffused into the solid. So there are 5 methods through which all 5 methods can act simultaneously, or maybe one method can act at a time. Okay, and most of the cases that the all 5 methods can be seen in the diffusion. Diffusion of 5 methods can be seen in the solid state diffusion phenomena. Okay, any question? Like it is very similar to the thing. If you are in a concert and you want to go to the go towards the stage, then you push someone, and someone goes forward, someone goes backward. Okay, something like that. Okay, just change of position of the atoms. Okay, that's how you move. If you have a tendency to move towards the state, then you move very fast, and then the other people actually leaves you the space. Okay, that's how the atoms also diffuse in the solid state. Okay, this is the microstructure of solid solution alloy. This is which is very uniform, and you will see only single phase in here. At the room temperature, you will see a single phase with the grain boundaries where the atomic arrangement is kind of different. Okay, but it will have the grain boundaries will also have the same composition, but it will show differently because of the light reflection and imperfect crystal imperfection. And this is the deviation from the deviation of the type 1 diagram. Sometimes the type 1 diagrams can have a point like this. Okay, it might show it, and this alloy will actually give you a unique melting point temperature. That means the solidification will occur at this temperature constantly, but this region there will be two phase, this region there will be two phase, and this single point can sometimes also be higher than the melting point temperature of both. Okay, so these are the deviation from the regular. If you look at the regular type 1 diagram, it will be like that, but sometimes it can also be like this. And this alloy, this alloy which have a constant melting point temperature is called pseudo eutectic alloy or congruent melting alloy. So this is kind of a compound is formed in this region. Okay. Okay, that's it for today. We'll discuss type 2 in the next class, because I have a defense meeting at 10 o'clock. So I can continue more from here. So, okay, in the next class, we'll discuss about type 2 diagram.